Hello, my name's Aminat Lola Shalebo, but my patients call me either Dr. Lola or Dr. Lola, depending on which languages they speak. I'll answer to either. My patients are children with potentially blinding disorders who are looked after at Great Ormond Street Hospital, where I work as a consultant paediatric ophthalmologist. I'm also a researcher at the UCL Great Ormond Street Institute of Child Health, and I'm funded primarily by the National Institute for Health and Care Research, or NIHR, which is sort of like the research arm of the NHS. I'm also lucky enough to have been funded by other groups, which are shown here on the first slide, and include the Academy of Medical Sciences, Fight for Sight, and the Wellcome Trust. During this talk, first, I'll give some background on childhood uveitis. Then I'll talk about eye imaging and how it could help. Then I'll talk about how we designed and ran the Zooniverse project. I'll share some findings from the project, and I'll finish off with our next steps. There is a shorter talk available, and you'll find it wherever you found this video. It takes a village to build anything important, of course. My village is made up of lots of people, and I particularly want to shout out on the left-hand side, from top to bottom, Katie, an eye health specialist, and Harry, an eye doctor, both at Moorfields Eye Hospital. On the right-hand side, from top to bottom, Jugnu Rahi, a professor and eye doctor, also at UCL and also at Gosh. And at the bottom, Lima Zulu, that's a username for an amazing Zooniverse volunteer who helped to support and manage the study on Zooniverse. Let's talk about childhood uveitis. Uveitis is actually not one disorder, but a whole host of disorders which all share this one important thing: inflammation inside the eye, or intraocular inflammation. The uvea is the middle lining of the eye and the red layer in that diagram. Inflammation is the body's healing or fighting response, and in uveitis, this healing, this fighting is happening inside the eye, and it's happening for no good reason that we can see. And the eye ends up getting caught up in friendly fire. The inflammation can cause damage inside the eye, and that can cause sight loss. About one in every 1,000 children in the UK has uveitis. Although it's fortunately rare in children, uveitis is much more common in adults. It's actually the most common reason for an adult to go to an emergency eye unit in the UK. Sight loss happens either because the uveitis is picked up too late. It can be silent, so the child and family don't know it's there until the friendly fire or inflammation has done damage that causes sight loss. Sight loss can also happen because we don't get the uveitis under control. That can be because the treatments we use aren't working, or they stop working in that child. Some visual loss occurs in as many as 1 in 5 affected children, and the disease can remain active throughout life, really, into adulthood, so it can be a lifelong disorder for some people. The majority of children with uveitis have idiopathic disease. That means we don't know why there is inflammation in the eye. Many have an associated disorder, with the most common being a juvenile idiopathic arthritis, or JIA. JIA is the commonest inflammatory disease of childhood affecting the joints. The drugs we use to control uveitis are called systemic immunosuppression drugs. Children get injections or capsules or syrup to use every week or every few weeks for a few years to keep the uveitis controlled. Sometimes they need to come into hospital for infusions via drip to keep the uveitis controlled. We choose these drugs in a trial and error approach, which means that we try one, and if that doesn't work, we move on to another. And if that doesn't work or it stops working, we move on to another drug. We're lucky to have more drugs to choose from than we used to, but it would be good if we knew from the beginning which drug was the best choice. We've asked children, young people and their families about their priorities around which questions to answer for uveitis. They want us to be better at diagnosing and monitoring disease, better at predicting outcomes, and better at choosing treatments or therapies. So families have told us that we need to be better at picking up and monitoring uveitis, and we agree. We currently detect and monitor using a microscope called a slit lamp that doctors use to look inside eyes and count the number of inflammatory white blood cells they can see floating around that shouldn't really be there. Right now, we have a slit lamp by microscope to assess disease. So there I am using one in the picture on the left-hand side. And in the pictures on the right-hand side is a magnified view that I have of the front chamber of the eye. And for this eye, it's full of inflammatory blood cells or white flecks floating about in what should be a quiet black space. We assess disease using the most clearly visible central section of the front of the eye. That's less than 1% of the entire volume, but we need to use an area that we can really see well and measure well. When specialists do this test, however, so if two eye specialists looked at the same eye, they'd really only have a 60% chance of agreeing with each other about how active disease is using this slit lamp method of examination. Optical coherence tomography, or OCT, is a non-contact imaging camera that's revolutionised how we look at diseases affecting the back of the eye. Now machines can also take really detailed images of the front of the eye. You can hopefully see the inflammatory cells as hyperreflexes, really bright dots in the black space indicated with that yellow line in that image. We've been working hard with lots of help from patients, so the children and young people and their families, to build an understanding of the best ways to use OCT to detect and monitor uveitis, and potentially even more. And here are those hyper-reflexive or bright white dots magnified. We've done this work across different types of OCT machines, building our understanding and building our expertise. We now know some things you have to know before you can trust any test. We know it's repeatable. That means that we know that if you do it twice, it agrees with itself. We know that it correlates with clinical grading, so it generally agrees with what a doctor can see. And we know that it's responsive. That means that when a doctor says there's been change, the imaging also picks up that change. We also think that the scans can tell us more about uveitis than a routine slit lamp examination could. For example, the size of the cells inside the eye might hold valuable information about what type of uveitis that is, and that means it might hold information about what sort of treatment that child should have. We also know that getting more and more images from the eye, from one eye, to some extent, gets you a better idea of what's going on inside that eye. But we also know just how long it takes for humans to look through all those images to analyse them. This is what we do for each image we get from the eye, and we can get hundreds from each eye of each child. An image grader assesses the quality of the image. Is it good enough to tell us what we need to know? Then they draw the region of interest, where in the scan we should be looking for cells in the image, in yellow in that diagram. The image is then changed from shades of grey to pure black and white. We call that thresholding, helps the cells to really stand out. We then use a computer program to detect how many cells are in the region of interest. It can take quite a while. We're building a system to do this automatically, but we need to teach that system using images that have already been labelled by a human. And that's where the Zooniverse Citizen Science Project came in. We asked citizen scientists to look through images from children with and without uveitis and help us with different analysis tasks. One of these was judging the quality of these images as good, poor, or limited by some sort of artifact or image error. We also asked them to tell us what sort of image error they could see. They classified artifact or image error as being due to movement. So in this image, there's been a small movement during the scan, and that's why there's that step in the structures in the middle of the image. They were asked to tell us if they saw lots of movement, and also these white splodges, which you can see in this image, which are due to eyelashes. Sometimes the eyelash artifact is quite subtle. So, for example, here, where the eyelash splodges are quite small and appear to be coming from inside and not actually outside, which is where they really are, of the eye. Sometimes you can see this flare or glare signal, which is due to an aiming light from the OCT camera shining on the eye in just the right or wrong place. Citizen scientists were also asked to draw the region of interest and to tell us where they could see any cells in the image. The project went live in June 2022 and we had a great deal of interest, and we are so grateful to the almost 3,000 volunteers who helped us to label these images. Here are some details about data management and analysis for those who are interested. And do remember to get in touch with me via my email, which is on the end of this presentation, if you have any more questions. So what are we finding? Well, this is a confusion matrix, a way to look at findings from what the most popular response from the citizen scientists was and compare it to what the experts said about the images. Okay, so of the 313 images that the expert said were good, so that's the first column with all the numbers in, most of the citizens, 272, the number in bold, agreed, although some said that the image was limited. But crucially, they didn't say that a good image was poor. And of the 278 images that experts said was poor, citizen scientists from Zooniverse agreed on 209 of those images and only completely disagreed, that is, said that a good image was actually poor 8 of those 278 times. And if we changed the citizen science labels into scores and develop thresholds for those scores, we can get perfect agreement on good versus poor images between experts and citizen scientists. We also looked at how much agreement there was on the type of artifact present. We used something called a kappa score to measure agreement. So a kappa score of about 0.61 to 0.81 is substantial agreement. Anything over that is almost perfect agreement. Citizen scientists achieved substantial agreement with experts on almost all of the artifact measures. The next step is looking into possible reasons why some citizen scientists perform better than others. Do they learn to do better over time, for example? Does the type of image they're seeing help? We're also completing some analyses on the agreement between citizen scientists and experts on that region of interest that they drew, and also the cells they're seeing. We're already pretty confident, though, on labels about quality and artifact. And once we understand exactly how reliable the other labels from citizen scientists are, we can really superpower our work on using this OCT imaging to improve outcomes in this blinding childhood disease. Thank you for your attention and your interest, and if you're one of our Zooniverse citizen scientists, thank you so much for your time. I also want to acknowledge and thank my funding sources and my wonderful collaborators, pictured or described here. Thanks.